Thanks for the introduction. I'm Chenhao. I'm really excited to be here to present the work Arbiter. This is a joint work with Anand, Hao, and Gennady, who is my advisor at University of Toronto. Today, designing DNN hardware accelerators is a hot research area. These hardware accelerators leverage various hardware-level optimizations to speed up the training process, such as low-precision arithmetic and sparsity-aware processing. However, these optimizations may have non-trivial effects on model accuracy. And that brings a new problem. How to accurately estimate the effects of these optimizations? Existing approaches to estimate these effects are either slow, expensive, inaccurate, or hard to use. So we propose Arbiter. Arbiter is a fast, easy-to-use emulator for DNN accelerators, and it's open-sourced. It achieves numerically accurate emulation with the aid of machine learning compilers. We conduct extensive case studies using Arbiter on popular benchmarks. DNN training workload can be extremely compute-intensive. Therefore, designing specialized hardware to accelerate DNN training has become an active research area. As DNN models are often tolerant to inaccurate computations and errors, hardware accelerators often leverage many hardware-level optimizations to accelerate the training process. And the most commonly used ones are low-precision arithmetic, approximate computing, and sparsity-aware processing. Low-precision arithmetic is to use low-precision data formats for computation. Instead of using FP32, which is the standard format in DNN training, people would use FP16, bflow16, TF32, etc. There are also other floating-point formats, but with different widths of exponent and mantissa, each making different trade-offs in the range and precision of values it can represent. The optimal format is still an open problem. There are also other formats like fixed precision or POSIT used for training. Using shorter formats allows hardware to provide higher processing power, and it takes lower memory footprint. Next is approximate computing. As nonlinear operations, such as hyperbolic tangent, sigmoid, GLU, are expensive and difficult to implement on the hardware, we could replace those with the approximate version to achieve better performance. In the meanwhile, it could also reduce the chip area. There's also sparsity-aware processing. People design specialized cores to accelerate the data that fits certain sparsity patterns. And one kind of sparsity pattern is 2-to-4 sparsity, which means out of 4 contiguous values, 2 values are non-zero. To enforce a 2-to-4 sparsity pattern on a dense matrix, we scan each 4 contiguous values, find the 2 with the least absolute value, and prune them to be 0. We keep doing that until we finish scanning the whole matrix. It then can be leveraged by certain hardware, say NVIDIA sparse tensor cores, to skip redundant computation to accelerate training. Although these optimizations provide acceleration opportunities, they also have non-trivial effects on model accuracy and convergence. For example, training ResNet 50 with FP32 could reach about 75% accuracy. But when using FP16 to train, the convergence is slower, and the final accuracy drops about 4%. This phenomenon can be even more serious and could even cause certain models not to converge. As manufacturing hardware is extremely lengthy and expensive, people need to decide the trade-off between performance and accuracy before manufacturing the hardware. So without real hardware equipped with these optimizations, how do we know the effects of these optimizations beforehand? One way is to use software-based simulators, such as GPU sim and multi-2 sim. The problem is it has a huge overhead. Our empirical result shows that for one matrix multiplication operation, GP-GPU sim is 5 orders of magnitude slower than bare metal GPU. Considering the fact that DNN training itself takes hours to finish, even with very powerful hardware, this overhead makes them impractical to use for DNN training workload. What about FPGA-based prototyping? It's another standard approach used for hardware verification. However, to reliably implement hardware features on FPGA devices, it takes huge engineering efforts. It also requires special expertise and infrastructure, and it's often very expensive. Recent work have proposed DNN emulation tools that are specifically designed for analyzing low-precision training, such as TensorQuant, QPyTorch, and GoldenEye. Despite being a promising approach, current DNN emulation tools suffer from a major limitation. They emulate at the granularity of layers in DNN models. Take a computation graph. They would only convert the final result of every layer to low precision, but the actual computation of each layer is still done in IP32. Such coarse-grained layer-wise emulation cannot accurately emulate low-precision training. We found when using QPyTorch to emulate FE16, the error of one single convolution operation could be up to 16%. We also trained ResNet 50 with QPyTorch emulated FE16, and we found the training curve matches with FE32 result instead of FE16. Since previous coarse-grained emulation does not work, we made a key observation that to achieve numerically accurate emulation, it takes more fine-grained manipulation of algebraic functions. Therefore, we took a compiler-based approach. Modern machine learning compilers operate on intermediate representation, which is a concept set of primitive operations, making them particularly suitable for fine-grained manipulation. Moreover, it is model and hardware independent, so it's easy to extend to other models and support other hardware-level optimizations. Based on that, we propose Arbiter to achieve fine-grained numerically accurate emulation. Arbiter is designed to provide easy prototyping to users and has a low overhead. So now let's dive into how Arbiter works. In order to specify these hardware-level optimizations, we expose 2 kinds of emulation policies to users. For low-precision arithmetic and approximate computing, we provide D-type policy, where user could specify a name of it and say custom type, and in the meanwhile, provide implementation of primitive operations, such as from float to float, which are conversion between FE32 and the specified type. Arithmetic operations, such as addition and multiplication, and mathematical functions like hyperbolic tangent or exponent. There are only a few such operations for users to choose to implement. Arbiter makes very few assumptions about the data format or the approximate computation operation. Therefore, it could support a wide range of arbitrary numerical formats and customized operation implementations. For emulating sparsity-aware processing, we provide a mask policy, where users specify an N and M to configure arbitrary N2M sparsity pattern. User would also need to provide a scoring function to decide how to prune values. Arbiter is built on top of machine learning compiler. Modern machine learning compilers, such as XLA, TVM, and GLOW, take a computation graph, transform it into hardware-independent IR, perform certain analysis and optimizations on top of that, ultimately lower to hardware-specific kernels. Built on top of machine learning compiler, Arbiter primarily performs 2 operations. First is arithmetic rewriting for emulating low-precision arithmetic and approximate computing. The second is memory access rewriting for emulating sparsity-aware processing. Originally, a dense layer will be lowered to multiply-add operation on FE32. And in low-level IR, it will perform a multiplication and addition operation. After user declare the D-type policy, they can specify that policy in any layer they want, to incorporate the policy into the computation. Arbiter will then rewrite the high-level IR to automatically insert conversion from FE32 to the specified type and rewrite the multiply add to perform on custom type instead of FE32. It then lowers these operations to primitive operations of custom type, such as from float, multiplication, and addition. The implementation of these primitive operations were provided by user as part of specification of the D-type policy, as mentioned earlier. By doing so, Arbiter incorporates the user-provided primitive operation implementations into the main computation and compiles it into hardware-specific kernels. Similarly, Arbiter overrides the memory access operations to enforce sparsity patterns on weight and gradient matrices to enforce sparsity-aware processing. Whenever the matrices are read during the training process, Arbiter dynamically generates the corresponding mask according to user-provided mask policy and computes the element-wise product between the mask and the access matrix. Arbiter then replaces the access to weight matrix with the mask weight matrix. This approach allows Arbiter to preserve the original matrices to handle dynamically changing sparsity pattern during training. Let's now take a look at an evaluation and how Arbiter could help users to explore the effects of optimizations. In this work, we focus on 3 important kinds of optimizations, namely low precision arithmetic, approximate computing, and sparsity-aware processing. But for the purpose of this talk, I'll be focusing on low precision arithmetic. Feel free to check the paper for other 2 kinds. We evaluate on 4 models, including ResNet, which is a convolutional neural network for image classification, GNN, which is a graph neural network for node prediction, Transformer, which is an attention-based neural network for sequence classification, and CRN, which is a recurrent neural network for language translation. We evaluate on 4 2080 Ti GPUs, and the runtime we use contains Catalyst 2.6 and TensorFlow 2.4. For our evaluation, we need to answer an important question. How accurate is Arbiter? We tried FD16 matrix multiplication and 3x3 convolution on 128 by 128 matrices and found Arbiter is bitwise accurate. We further trained ResNet 50 using Arbiter emulated FE16. We've shown that prior work emulated FE16 does not match native FE16 results. But when emulating with Arbiter, both convergence curve and the highest validation accuracy match closely with native FE16 results. Therefore, we could conclude that, as opposed to prior work, Arbiter can accurately mimic the numerical behavior of hardware. Next, we want to see the overhead of Arbiter. We've shown that for one single matrix multiplication operation, software-based simulators have 5 orders of magnitude slowdown, while Arbiter is only 2.6 times slower, significantly faster than software-based simulators. When training GNN model using Arbiter emulated types, we found Arbiter could have slowed down up to 6 times. So Arbiter could achieve numerical accurate emulation with feasible overhead. We conducted sensitivity study of low precision training. From the result, we could see for ResNet 18, using 6 bits for exponent and 6 bits for mantissa, in total 13 bits is enough for it to train to FE32 accuracy. Similarly, for other models, we found for Transformer, CRNN, and GNN using 11 bits, 13 bits, and 10 bits are sufficient to train to FE32 accuracy, which are lower than the standing floating point format like FE32, BFloat16, and TF32. We also noticed that certain models, such as GNN and Transformer, require less precision than the others. These results illustrate that Arbiter can allow hardware researchers to conduct accurate analysis about DNN model convergence and accuracy. We next investigate how subnormal mode would affect training. Subnormal mode is a special value encoding in floating point format, and it could handle values below the normal range. It enabled representation of extremely small values to alleviate the problem of underflow. But the drawback is it could take larger chip area. We repeat the previous sensitivity study with and without subnormal mode turned on. We found for ResNet 18, the accuracy achieved without subnormal mode is not significantly different from the result with subnormal mode when exponent width is greater or equal to 6 bits. We observe the same phenomenon for other models too. So from the result, we conclude that when exponent is wide enough, subnormal mode is not needed. Furthermore, we investigated POSIT format for DNN training. POSIT is an alternate format aiming to replace floating point. It was designed with an increased dynamic range. And prior work claims that it could improve model accuracy. We tried running different configurations to get highest accuracy for a total width of the data format. And we found for transformer, CRNN, and GNN, the highest accuracy reached using POSIT and floating point are all similar. So contradictory to observations of prior works, POSIT does not yield significantly better accuracy compared to floating point. We have additional details in the paper that I didn't get a chance to cover in this talk, and I encourage you to check it out. We can see additional results and read an extensive discussion section on how Arbiter could extend to other data formats, other deep learning frameworks, and other hardware features. To summarize, since hardware-level optimizations affect model accuracy, accelerator researchers need help to know their effects accurately. Existing methods to analyze these effects are slow, inaccurate, or hard to use. Arbiter achieves numerically accurate emulation with the help of machine learning compilers. Arbiter is user-friendly and has low overhead. We show through a series of case studies that Arbiter is helpful to accelerator researchers. Arbiter is an open source tool that you can find on the GitHub page. It has also passed the artifact evaluation. Thank you for listening, and I look forward to seeing you at the poster session tonight.